This is Gabriel Parmer, and I'm going to be talking today about our work on embedded WebAssembly to provide practical software fault isolation to microcontrollers and small embedded systems. This is work done between George Washington University and ARM. Traditional embedded microsystems have had it easy in many ways. They've been closed systems by and large, which means that they're relatively self-contained, and code only needs to consider their set environment, all of the pieces of software and hardware installed on that embedded system. In this way, they're relatively simple and customized. A single company was largely responsible for integration of most of the code. They would contract subsets of the software to different vendors, but then relied on integration certification to get trust in the overall execution of the system. However, modern embedded systems have started to look quite different. The Internet of Things is an example of this trend in that they're pushing up the complexity of systems while throwing away that assumption about being a closed system. So they're adding networking that's often exposed to the internet. With network access often comes the adversarial inputs from whoever might send packets over the internet. They've also focused on supporting agile development and require inexpensive software and hardware for the mass market. What this means is that the integration of untrusted code has been increasingly more of a focus, and that includes a lot of open source code. This means that certification has been much more of a challenge and is often not attempted at all. So if you don't have certification of your software, and if you are exposed to the internet, isolation tends to be one of the normal ways that we deal with the systems, that we protect systems. So if we have untrusted software, it's potentially buggy and uncertified. If we have untrusted inputs, then it's potentially malicious that can lead to compromises. This is made all the more difficult because microcontrollers lack some of the normal protections that you might have in such systems, such as no address space, layout randomization, often no hardware protection features, and certainly very little memory with which to work with. So the goal in this type of environment is to isolate the system from potentially errant effects of complex and uncertified client code and from the outside environment. Isolation is the key here. However, isolation is very difficult in a lot of these systems. They might support some form of hardware-provided memory protection, usually in the form of a memory protection unit, an MPU, which is quite unlike an MMU that many of us are familiar with that provides virtualization. MPUs focus on subsetting access to physical memory. The downsides of MPUs are that they do not provide virtualization. They do not provide virtual addresses, so they are not nearly as flexible in many ways. Obviously, if you're relying on an MPU to provide isolation in your system, you're relying on that hardware support, which has a much higher probability of not being supported on microcontrollers than in normal systems. And often they mandate a very specific isolation structure within the system, which means that if you're using a middleware that requires one structure, it might not be compatible with a RTOS that requires another. These systems often rely on interpreted languages as well, such as JavaScript, Python, and Lua. They're very common in microcontrollers, but these are not a general purpose solution because they're slow and generally unpredictable due to garbage collection and interpretation costs. So another option that we're investigating is the use of software-based fault isolation, or SFI, within these systems. And the high-level idea behind SFI is that they provide the pair of memory safety and Cntl-Flow-Integrity for code to provide a sandbox within which they can execute. Memory safety prevents accesses outside of the sandbox by typically using bounds checks. And Cntl-Flow-Integrity usually tries to ensure that branches and jumps cannot be taken that are not actually intended by the compiler. So we want to limit the control flow to what has been analyzed by the compiler. This research takes this notion of software fault isolation and uses a standard called WebAssembly and investigates whether we can provide embedded WebAssembly for efficient and predictable software isolation for research-limited microcontrollers. I'm going to go into a little bit of a background about what sandboxing means, and I'm going to contrast it to type safety, which is something that many people are familiar with. So here we have a very simple data structure, which is a struct or an object that has a pointer to an array. This might be an image structure that has a pointer out to the data for that image. And you can see we might have code where we get the image, we look up the data, the array within it, look at the 6th item, and see what the red value is in it. Now, how do we provide protection for this type of system in a type-safe system? Well, the image pointer is often guaranteed to be valid because of garbage collection. This is not something that we typically want in microcontrollers simply because of the unpredictability and the overheads therein. When we look up the mem field within the image structure, that often requires that we understand what the struct is, or what the type is of the image structure, so that we can figure out what that offset is and check whether it's at a valid offset. And when we look up an item in an array, we often need to provide bounds checking, which is done taking a part of the type of the array, which is its size. So this is obviously very successful. Java uses this, Python uses this, a lot of languages use this, but they make a lot of assumptions on the system. For instance, they often require garbage collection. There are some systems that are moving away from this. They often require a defined object protocol, which essentially means that you understand the layout of your structures and the types therein. And they require type-aware bounds checking. This requires a lot of type awareness that does not allow generic code outside of the intended language to run within that object model. Sandboxing, on the other hand, essentially says that the code running in the sandbox can do more or less whatever it wants within the sandbox. However, it's only allowed to access memory up till the maximum size of the sandbox, which you see here. So when we're looking up image, mem, red, all that we're doing is bounds checking within the overall range of the sandbox, not necessarily within the language-specific data structures. If we look at what this might look like, we're taking the code on the upper left, which is just dereferencing a pointer x, which is pointing to an integer, and writing it into y. If you look down from that, the code that might be generated would be some sort of a load that is dereferencing the pointer and writing into another. If we replace that with something that might include this bounds checking, then it would add a certain number of instructions for calculating what the maximum bound of memory we might access is, the reg max. Here, by the way, the % signs designate the register name. So we find the maximum byte that might be accessed, determined by the size of x, and we compare that to the maximum bounds of the region that we're allowed to access within the sandbox. And if we're trying to access beyond that maximum bound, we trigger some sort of an exception handler. Otherwise, we do the load. So we can deal with bounds checking by simply adding checks within the code, either by the compiler or the assembler. So these do not necessarily require garbage collection, the object protocol, or type-aware bounds checks. All that they require is a compiler or assembler to generate those load and store protections. The downside is that this can be often relatively expensive. The focus of software fault isolation is then to constrain the errant behavior of the system to the restricted range of memory within the sandbox. This isolates the faults that the sandbox may exhibit from the outside system, but allows the sandbox to do essentially whatever it wants within that sandbox. This unrestricted access to memory within the sandbox is key for embedded systems because it means that we can actually execute unsafe code such as C, C++, and even safe code or well-typed code at the very least, such as JavaScript, Java, etc., within the sandbox because we don't require large runtime assumptions. Cntl-Flow-Integrity is something that I'm not going to go into much here, so I just quickly want to go through this list. How we can hijack the control flow of an existing system is using things like buffer overflows that essentially try to control the return pointer from a function, often by overrunning some sort of a stack allocated array. They can include things like heap spraying, which is meant to override function pointers within data structures so that when we invoke them, they go to some sort of a adversarial function, or return-oriented programming that essentially use buffer overflows in ASLR protected code. Now, the challenges of providing SFI on microcontrollers go beyond what the challenges are on normal systems. The code size blow-up due to inserting all of those range checks can be significant when we want to check whether we're safely accessing memory within the sandbox that's generating code which can blow up the code size. And microcontrollers have generally restricted flash sizes between something like 128 and 2 to 4 megabytes. So not a huge amount. We also want to effectively use SRAM, which can be difficult. We'll see later that some sandboxes, for instance WebAssembly, make the assumption that we can increase memory by 64 kilobytes at a time. 64 kilobytes is larger than the RAM size on many of these systems. Additionally, the code slowdowns due to these safety checks can be significant, and unlike larger systems, they're not hidden by the microarchitectures of these microcontrollers because they're generally pretty simple five-stage in-order pipelines. Additionally, we want to ensure that the predictability of the generated code is assured, that these bounds checks are not unpredictable, as would be the case if we required something like garbage collection. So we use WebAssembly as our base for a standard software fault isolation infrastructure, and we attempt to make WebAssembly essentially run in a sandbox on microcontrollers. The benefits of using a standardized software fault isolation technology is that there's a large ecosystem for them. So WebAssembly itself is a generic portable assembly language. It's language agnostic, so you can compile C to it just the same as you can compile JavaScript to it. And it's a increasingly common compiler assembly target. LLVM can target WebAssembly as one of its outputs, and LLVM can compile tens of different languages. So inevitably, we can support tens of different languages down to WebAssembly, which is quite nice. It's very popular. And historically, it's called WebAssembly because it's been focused on in-browser execution. Indeed, the most popular browsers now support WebAssembly for executing code alongside JavaScript. But it's been appearing increasingly in serverless domains, in edge domains, and on microcontrollers. If you want to learn more about WebAssembly, see webassembly.org. WebAssembly uses memory safety in a way that I previously discussed by inserting bounds checks in some way, but how it provides control flow integrity is slightly more intricate, and I want to give an intuition of how that's done here. So if we take our image format that we had before and expand it so that the image structure includes some sort of a function pointer called getFormat, and it is expected to return the format, a string for the format for each of the different image formats that the system supports. So in this case, there's a TIFF_getFormat function that returns TIFF for a TIFF style image. And you can see the code on the left. We're essentially just calling that function pointer to be able to copy that string out into a stack allocated array. Well, if you know anything about buffer overflows, this might already ring some alarm bells for you, because we're now copying an unrestricted size into a stack allocated array, which can be unsafe because it might overwrite the return address. So what WebAssembly does is it moves all local allocations of potentially referenced structures from the stack into a data stack in the linear memory. Second, all function pointers need to be, well, let me back up. What that means is that we can't overwrite the return address in the execution stack simply because we're never accessing the execution stack directly from within the sandbox. So what I'm showing here now is another extension whereby all function pointers, instead of directly pointing to the functions themselves, point to an offset within an indirect function array provided by WebAssembly, provided by the WebAssembly runtime. And that's the green array here. So get format is now pointing to an offset, the third item in that array, which points to the TIFF get format function. So we can do type checking here and ensure that we're actually calling a function that we're supposed to be able to call at this point. So these two features alone ensure control flow integrity within WebAssembly. So WebAssembly is really just a combination of the memory protection that we talked about earlier, the memory isolation, and these control flow integrity features that we see here. Provides memory safety by restricting loads and stores to what WebAssembly calls a linear memory, and control flow integrity is provided by this combination of a data stack and checking of function pointers. Now, the challenges of getting WebAssembly working on microcontrollers is that linear memory for WebAssembly is always extended in 64 kilobyte increments. Our system, eWASM, simply changes this to be on much smaller increments. Additionally, the standard doesn't specify how bounds checking should be performed, what the implementation should be. So we investigate multiple implementations of that trade between memory consumption and performance. So this research then provides investigation of designs and implementation of WebAssembly sandboxes that are low overhead, predictable, and efficiently use the system's memory. eWASM fits into a relatively large ecosystem around WebAssembly. On the far left, you see blue boxes that are each of the languages that the compilers in the purple boxes use to compile into WebAssembly code, the generic assembly code of Wasm. And you can see LLVM compiles from a great many languages into WebAssembly. eWASM is a combination of the Awesome compiler, which we've implemented as part of the system, and the eWASM runtime. The eWASM runtime defines how the bounds checks are performed. It implements the indirect function call table and type checks around that, and it defines a set of system APIs that can be used to invoke from within the sandbox to the surrounding systems. And we, in this case, provide some free RTOS callbacks so that we can execute a process abstraction within free RTOS. The Awesome compiler outputs LVM IR, and the combination of the runtime and that IR is compiled together with LVM into something that can run on Cortex-M style processors. And we've executed this on Cortex M4s and M7s, but it should run on most of the processors. So, we've investigated how to do multiple different styles of bounds checks, and I'd like to walk through a few of those here. The first design that we studied is in some ways the most straightforward, and its goal isn't to ensure that loads and stores within the sandbox remain within the linear memory or trigger an exception otherwise. So this first design simply does conditional checking on each dereference, each load or store, to make sure that it stays within the bounds. This takes about 8 additional instructions for every load and store and is quite accurate because it can take the linear memory size, whatever it is, and checks whether our accesses are within that. And you can see some rough C pseudocode for what that might look like. At the highest level, it simply ensures that the address is within the linear memory or triggers an exception. The benefit of this approach is that it provides exact and precise memory checking. So linear memory can be essentially any value, and we check to make sure whether the addresses are within that. However, it does have significant overheads because it generates 8 additional instructions for loads and stores, which both decreases performance and increases binary size. The second design that we looked at was to use wraparound. So what this essentially does is it assumes that linear memory is always a power of 2 size, and will take the addresses that we're trying to access on loads and stores and will wrap them within that power of 2 size just using masking So you can see approximation of that functionality in C on the right. This includes and adds about 4 additional instructions. And the plus side of this is that it's relatively quick. It does add overhead, of course, but not too much. It doesn't add that many additional instructions. The downside is, of course, that the linear memory has to be a power of 2 size. So this can add significant internal fragmentation within the linear memory. And it also changes the standard behavior of WebAssembly. Whereas normally accessing memory outside of your bounds causes an exception to trigger, this has undefined behavior in that it wraps back within memory. The last design that we implemented was software page tables. So this was, of course, inspired by hardware page tables, and it includes a relatively complex operation that converts between a virtual linear memory address to an actual range within the real memory on the system. The big benefit of this approach is that it enables non-contiguous memory allocation for a Wasm sandbox. So it might be more suitable for dynamic code that you don't necessarily know the maximum linear memory size. So it has relatively low memory overhead in SRAM if we use relatively small pages, and it provides non-contiguous allocation of that memory. However, it does have a relatively high overhead because we are actually doing lookups on software page tables on each load and store, and has a much, much higher binary size simply because of all of those lookups being inlined into the code. Now, we're going to look at some results here, some experimental results. We look at Polybench, which is a collection of benchmarks, which are all shown here. We use Polybench simply because the original Wasm paper used Polybench, so for experimental parity, we evaluate in the same way. You can see that there are many, many different results here, and I'm not going to go into all of them. You can see on the far right, there is this bar that takes the average of all of the preceding bars. I'm going to focus on these average values to present them tersely here. Please see the paper for a more in-depth evaluation of the all results. So on the top table here, you see the execution slowdown versus C. So this is versus if we were to compile with the C compiler. And you see that the wrapping bounds checking approach has about a 40% slowdown versus C. Conditional has a 67% slowdown, and software page tables are about 4 times slower than C. So you can see that trade-off in action here. In terms of ROM consumption, this is the binary size. We see that C for Polybench has on average about a 20 kilobyte consumption, whereas all of the Wasm, eWASM implementations have a significant blow up over that. Wrapping is 86 kilobytes, conditional 133, and so on. Software page tables are very, very large at over 600. If we look at the RAM consumption, the SRAM consumption for linear memory and other structures, we see that C is relatively small, 16.1. This is largely because it can put its read-only memory into flash, whereas Wasm cannot. It has to be in linear memory. So we see that wrapping blows up significantly because it essentially has to round up to the largest power of 2, which in many of these applications is either 128 or 256, whereas conditional and software page tables are significantly slower. So summarized at the bottom, we see that wrapping is the fastest and relatively competitive to C, whereas condition is fast, though not quite as competitive, whereas software page tables are relatively slow. I did not put this as a red X, which denotes bad, simply because if we compare versus some of the interpreters, software page tables compare pretty favorably. In terms of ROM size, binary size, the wrapping does decently. Conditional increases that because of the increasing size of the bounds checks, whereas software page tables are very large. In terms of RAM efficiency, the wrapping has a significant amount of internal fragmentation, so its increases are significant, whereas the others are not that bad. I do want to make a note here, and that all of the embedded Wasm numbers, especially for memory here, include an in-sandbox libc, so there's additional overhead for that, and the data stack. The data stack is counted inside of our linear memory in these results. However, none of these results, even for C, count the execution stack size. And that's simply because we wanted to be somewhat pessimistic in terms of our reported sizes, and we didn't want to penalize C in any way. Now, see the paper for a lot of additional results, including some applications that we studied in a comparison versus interpreter, and we've run this on multiple systems, including Cortex-M4 and M7s. Now, we did run into a number of places where the standards of WebAssembly were adversarial for us coming up with a good implementation. So we have a number of pieces of advice for the WebAssembly standardization for creating an embedded profile. This includes that read-only data. It would be really good if that could be included not in the linear memory, because the execute in place support within ARM processors allows us to put that read-only data in flash. So if somehow we could put it in flash, that would benefit the RAM consumption of these systems, possibly at the degradation of the bounds checking overheads. It's absolutely essential that we support multiple page sizes, and this is something that the WebAssembly standards have been talking about. And it also requires that we relax the specifications slightly and allow undefined behavior, such as in our wrapping results, for improper loads and stores. One thing that we did try to design was a co-design between the MPU and the bounds checking implementations, but we were not able to actually make that work for reasons that we go into in the paper. There's a fundamental limitation that prevents it from happening. So the conclusions of this research is that we have designed and implemented an efficient and low memory software fault isolation implementation for microcontrollers. We're the first system that we know that has implemented different implementations for bounds checking and compared and contrasted the trade-offs in terms of efficiency, memory consumption, and the failure behaviors, whether it's undefined or whether it causes an exception. And we've also provided access on microcontrollers to WebAssembly, which is a popular, active, and standard SFI mechanism. So hopefully microcontrollers can now benefit from the large endeavor that's being put into WebAssembly broader in the web and server space. If there are any questions or comments, I highly encourage you to ask within discussion systems. This is all open source code, so please go to our gwsystems.org and see the awesome work, which has embedded Wasm in it. We have support for a lot of different architectures, including most of what LLVM supports, so one's not listed here, but we haven't necessarily tested with one's not listed here. And we support a number of different contexts, including serverless, standalone, and eWASM. We appreciate your time and look forward to your questions. Thank you.